Hi everyone again. So I'm going to talk about rheological characterizations of 3D printable mixtures beyond flow initiation. So I picked the word flow initiation very carefully here. Probably everyone in this room would agree with the definition we typically use for the static yield stress, which is the stress required to initiate flow. And by the two prints that I have in example, we can somewhat assume the print on your left-hand side is the one that reached its static yield stress, where the one on the right did not reach its static yield stress. So I sort of want to start with the definition and sort of close with the definition, because I think we do need to update this definition and talk more about more than just the static yield stress for this behavior. So I'm going to try and just give some brief background on where does the static yield stress come from, where the structuration comes from. And I always like to refer to the work of Professor Roussel for this. And we can sort of look at this very quickly. So with the onset of water and cement interactions, we would start to have some colloidal interactions based on van der Waals forces and based on electrostatic forces. So we can sort of conceptualize that this is what we have between our cement and water system. Now, in few tens of seconds, we start to have dissolutions, which means ions are released into the water, and that creates some ionic forces and increases some of our forces. So this is where we sort of can appreciate our first static yield stress. We can call it at time zero. From that, we start to see that the static yield stress will start to grow, either when we start to have nucleates, so those are what we can refer to as these nano CSH bridges. And because these are of different type of chemical interactions, they are different stiffnesses, and sort of we can refer to them as a different structure. And so we typically refer to this as the rigid structure. Now, over time, we would start to have more nucleation and more growth, so there's more CSH bridges, and these CSH bridges starts to thicken in our cement. And over time, this keeps happening. Once we hit a certain amount of time based on our cement chemistry, we are now mostly looking at the growth of this and then the bridging between our particles. Now, because of this phenomena, if we actually try and measure the static yield stress of our cement in the rheometer, we can actually capture two specific peaks that will appear in our cement. The first peak will happen at a very low strain, so we're talking about less than 0.1% strain, and that's where we see the shift in our behavior. So we're going from a very stiff mixture to a less stiff one. Now, at that, we don't really have a flow onset. At least that's what we believe. And then we typically would say that the rigid network, so all the chemical hydration bridges have been broken, but the colloidal structure, all these other interactions, have not yet been broken down, and that's due to this different stiffness between these interactions. Later on, what we typically refer to in the static yield stress is when we go to that second critical strain, and that's within few percentages of our cement-based systems. Now, the static yield stress will sort of have both of these built in, because the rigid structure has to rupture before we can get to the colloidal structure in order to break it down. And I'm gonna just make sure that we're all just in agreement that typically what we refer to in static yield stress for flow onset is in this graph on the right over here. Now, 3D printing concrete really relies on that principle, is that when we have our bottom layer, as layers keep coming up, the stress keeps increasing on that layer. We want to make sure that we have enough initial static yield stress, so that would be our point here that we're starting, and then that we have enough structuration rate in order to keep that line above our red line. Hopefully they're not that close, right? But typically this is the bare minimum until we have the onset of hardening. Now this could be 1 layer, this could be 10 layers based on whether we have an accelerator or not, right? Now there have been work that start to look at what's happening to this rheology and what's happening colloidally and rigid, for the rigid structure during the stress period. So when I place my cement here and it's being sustained stress on top of it, what's happening to my rheology of cement? So there have been some work that looked at plain cement systems, and it basically showed that as we increase and impose a stress on our cement paste that is lower than the static yield stress, we start to see that the structuration rate is actually quite higher. So as you see from these curves, you start here, this is what we typically assume at rest. But if we impose some resting stress on top of these, we would see that static yield stress is actually growing at a much faster rate. And so this picture really can be imagined like this. As we place more layers, we would be structuring the cement much faster. And so there is a true static yield stress curve that we need to be able to predict. And predicting this true static yield stress can make a lot of differences in how fast we can print and how we predict our print performance. So to do this, I decided to go with a rheological profile, and I also wanted to look at other measurements. So the first thing that I did is I looked at a typical rheometer, and I applied these two rheological profiles. So the first one is what we typically use in a rheometer is we will just have some deflocculation, some resting condition, and then measure the static yield stress. And the second step, I wanted to impose a stepwise function of stress at rest that is below my static yield stress. So in this step, so we can assume in this step I will have 1,000 Pascal that happens in here at this time. So in this step, I will try and see if I keep this below my 1,000, where would my static yield stress be? And in some cases, I was able to go even higher. And when I quantify my data, I did not only quantify the static yield stress, I also looked at where that stress is happening, so the critical strain, and I also looked at the slope. And in this case, we can this is measuring the shear modulus, but we can very easily infer from it an elastic modulus. And for this, it was interesting not to look at typical cement pastes because we don't really use this in 3D printing. 3D printing has this advantage of having an order of magnitude higher static yield stress. We've been seeing static yield stress throughout the sessions on kilopascal of orders of magnitude. So I wanted to go beyond this and see what's really happening to the cement paste. So I looked at 4 different systems. The first one just had VMA, so a viscosity modifying admixture, because the system that I'm using and all the printers that I've used, you typically would run into some bleeding issues for longer printing, and VMA is one of the additives that we can use to mitigate all the bleeding effects. So my reference mix always had a VMA, and for this case, if you're interested in materials, this was just a cellulose ether of low molecular weight. The second mixture that I had, I went and added PVA fibers, and that was interesting because we typically would include the fibers to improve the mechanical properties, and there have been research that showed that it also will improve the rheology, especially with fiber alignment. The third mix, I added nanoclays. That's where I spent a lot of my PhD doing work on, where nanoclays are interesting because they improve the static properties without really impacting the dynamic ones. And the last mix is by trying to replace part of the cement with silica fume. And silica fumes were interesting because they are also very beneficial for the rheology, just like we saw from the previous presentations. And here I just want to make sure that all the water cement ratios were fixed at 0.4, and I'm still here measuring for mortars at a lower sand ratio. That's just because I want to be able to capture all of this with the equipment available for me. So we can look at what's happening with each of these mixtures. So rheologically, we can see that with a zero stress at rest, which is the point in orange, we can see that we can achieve somewhat of a 1200 Pascal, right? As I start to increase the stress, so if you remember, this is how much I'm applying per 100 seconds over 5 steps. When I keep increasing the stress at rest to sort of mitigate or mimic what's happening to my stress as the layer buildup goes on, we can start to see, for my reference mix, my static yield stress is increasing indeed, right? The other thing that was very interesting is that my critical strain was dropping for this mixture, right? So you can see sort of where these curves, and I like to plot my curves on the x-axis in the logarithmic scale, just because, as I mentioned, there's the existence of these two strains, and I really like to see that solid region very clearly. So you can see how much there is a shift in this happening to the left. The other thing that's interesting that's happening is my shear modulus is also dropping, right? So in this case, applying stress at rest, so mimicking what's happening to the buildup phenomena, we see the static yield stress is increasing, strain is decreasing, shear modulus is decreasing. Now in my second mixture, I saw somewhat of the same thing. The static yield stress also kept on increasing. However, my critical strain did not really change as much. 8% is within the statistical noise you would assume. And same thing for the shear modulus. So now with this rheological admixture, or this admixture that we're adding, the effect is now only at the static yield stress, and the effect on the static yield stress is much higher. So in the effect in here, around 200 and around 17% was only 40%, whereas in here I'm at 14%, but I'm increasing my static yield stress by 66%. Okay. The third one, which was a more interesting one, so nanoclays increase the static yield stress, as I said, significantly more than everything else, and we can reach a static yield stress of around 5400. When we start increasing stress at rest, it does not seem to be that sensitive to it. So it will increase it a little bit, but then it will sort of just plateau and live there. When I looked at the critical strain, the first two are within the statistical noise or close enough that I would not make a lot of meaning, but then we start to see that there is somewhat of a shift on decrease. The shear modulus mainly remained the same. Now also here we can see the different magnitudes that are happening, and I'll make a slide just to show the summary comparing all of these. The fourth mix, when we substituted with silica fume, we saw, again, there is more sensitivity, so we're increasing as we're increasing pressure, but it's not as sensitive. So here I'm increasing 11%, I'm only going 13%. So the sensitivity of my mixture, my 3D printing mixture, to whatever build-up process that I'm applying changes based on whatever admixtures. So how we create the static yield stress changes basically its reactivity to the print build-up process. For the critical strain, there was a drop, but then it remained very static, and the shear modulus with silica fume got affected significantly. So I almost lost 60% of my shear modulus. So sort of summarizing all these mixes and the three properties. With only a viscosity modifying admixture, the static yield stress goes up, but it goes up around 40%, but there's significant decrease in the critical strain and the shear modulus. With PVA, the effect was only at the static yield stress, and it was a very significant effect. With nanoclays, there was somewhat of an effect on the strain. There's really no effect on the shear modulus, and the effect on the static yield stress was not so sensitive to how much stress is being imposed. And in the last case, when we're looking at silica fume, there was a lot of decrease in my shear modulus and not a lot of gain in my static yield stress. So this is all nice rheologically, but what will this happen in 3D printing, and how does it really compare? So to do this, I went with the buildability tests. And because from what we saw before, there's two really modes of failure in buildability. One is around buckling, and the other is by static yield flow. And so I decided to do my buildability tests with two geometries. The first one, which is just a braced wall, so making sure that I have very small lengths that are unbraced. And then the other one is just by doing a typical cylinder where we have a longer unbraced length. So in this case, the cylinder is more prone to buckling. So when I'm seeing these reductions, I'm trying to see if the reduction in shear modulus is now going to interpret into loss of structural stability before I get to my static yield stress. And so with the cylinder, it was exactly what I thought. So with the VMA, with my PVA, and with my silica fume, I was buckling. So I had local buckling, and then this was literally on the onset before this whole thing buckled and collapsed. With the VMA and nanoclay, I was able to keep going until I reached the maximum print height of my printer. With my walls, I had static yield failure for both my VMA and my PVA, but both my silica fume and my nanoclay mixes actually went to as high as my printer goes. Even though in some cases I would have errors and I would have more material sitting, it did not really affect it. And so I was very curious to sort of compare these things together and sort of try and put everything together. And then here we can look. So this is the static yield stress for everything when we are not applying any stress at rest. And this is basically the results that we have from the buildability tests. So this is where all the prints failed, and this is what I can approximate the pressure of that bottom layer stress to be. So here we see with the VMA mixture, I actually was failing around my static yield stress, but when I looked at the wall, I actually failed at a much higher height, at a much higher stress. So my prediction that there's an effect of a higher static yield stress because I'm now doing layer buildup was actually true in this case. In the case of PVA, it wasn't as true. So, and the PVA is an interesting case, especially because of the fiber alignment. The way we can apply rheological measurements through the shear rheometer might not be accurate to represent what's happening to fibers because of the shear history that we put on into our sample. The nanoclay mixture, I could not really get too much out of it because none of it failed. And the silica fume was the one that's interesting. I was able to record this with less than 30%. So that huge reduction in my shear modulus was actually meaningful. That imposed stresses on my layers actually did decrease my shear modulus, and that was the reason I was starting to see local buckling effects come in play. So this is more or less just summarizing what happened. So if I look really close at it, my VMA mixture actually had two problems. When my critical strain dropped so significantly, I was able to capture this in video. Those cracks happened when the material was still wet. So because the imposed stresses on my mixture keep adding up, pushing the critical strain to a really low value, so this was happening around 0.17, I was actually cracking in tension. And that created those cracks before the material even have set, and then I had experienced the failure because now I have a very low shear modulus value. With the silica fume one, which was the interesting one, when I had the braced geometry, I had no failure, and in the other case, I had a complete collapse because this reduction in my shear modulus. That did not happen with my nanoclay mixture. Now this is all, again, very interesting, really nice, but I wanted to go further than this. How can I really quantify the static yield stress? And how can I quantify these with my printer? And so there's one test that was first proposed in 2020 by Jacket et al. And then it was again revisited by the Complier. And in this test, we basically can look at our extrusion when it's just lifted in air. And we can monitor the slugs that are forming. Now, we have to be careful when we talk about slugs forming. There's a certain conditions based on the diameter and the velocity that we're extruding, that we would have a slug by slug flow. So whenever we're within this region where we see complete fracture or necking, we can quantify this as slug by slug flow. If we go beyond this region, then we're no longer in the slug flow. Right? So this is the basis of this. So what I did, and to be able to analyze this, we can analyze it in different methods. And I was very interested in all these three methods. So we can either collect these slugs that are being formed as we're extruding our material and take their mass. And from their mass, we can get a shear stress, or we can use image analysis and get either the length based on a certain assumption of volume and density relationships, or we can go back and take the volume measurements of these slugs and calculate a static yield stress. And I wanted to do this for all my mixes. So to do this, we basically built a very simple MathCAD form where we take these slugs. This is just an example. I was using a much bigger nozzle in my methods. And I basically looked at the length of my slugs alongside the volume. But I also was interested in another phenomena. I did not only want the shear stress. I also wanted to look at the second property, which is my shear modulus. So I went and looked at both the necking angles, so the top angle and the bottom angle that are forming, and I looked at their comparison. So this is what we see for all the four different mixes. We see that the slugs are very long, but we also see different geometries between these slugs, right? This slug is much more angular compared to these slugs. And so when we look at these results, really, we see that the angle that we're nicking with actually corresponded to the shear modulus. So the lower this angle was, the higher my shear modulus. So we can actually back calculate mechanically what the shear modulus would be just from the angle of necking. The other thing that was interesting is by looking at the length or the volume measurement of the static yield stress, with length I was overestimating both the VMA and the PVA mixtures. But when I looked at volume to sort of account to these oddly shaped slugs, I can actually close enough capture the static yield stress. Now, I did the same study and expanded it much more on nanoclay just because I had a lot of access to a lot of materials. And I did the mass measurements of the static yield stress with the slug flow, and I was able to compare it to shear rheometry measurements. And here you can see with mass, it's quite accurate. So within 96% accuracy of fitting a lot of different mixes, we can measure the static yield stress in the shear rheometer and through extensional rheometry. However, the dynamic yield stress, what we would assume would correlate with the slugs, does not really correlate with it. And so I'm going to close up with very quickly in here. But with static yield stress, we can measure it in a lot of ways. We can measure it with shear rheometry, and then we can look at our shear protocol and the effect of rest. With extensional rheometry, we can look at slug length, slug mass, slug volume, and buildability we can look at all. So all of these are different ways to define static yield stress. In the context of 3D printing, really the one thing that's most meaningful is this. When we have a print layer collapse, that's the most one. So how do we measure it on site, and how do we measure it in lab during development? Because we need to be able to compare and contrast what we have and what we've done. And this is just another interesting, when we talk about the true static yield stress, when we keep adding more admixtures, especially when we start introducing a lot of polymers, the stress strain diagrams shift significantly. And currently we keep the definition of the stress required to initiate flow, and we define it as the peak stress. However, that stress now happens at very different orders of magnitude in strain. We can note in some cases, and I've been playing with polymers a lot, we can even have multiple peaks appearing. And so there is a great need to start to revisit how we define the static yield stress in terms of 3D printing concrete, and start to incorporate the effects of the strain and to incorporate the effects of the shear modulus. And so I believe we're running out of time, so this is basically summarizing what I've been saying. And lastly, I just have to acknowledge my coworkers, and I'll take questions.